For this game, we have the concept of Bayesian-Nash equilibrium. Because it was when it was introduced, it was assumed that the player follows Bayesian update of probability. Okay, so in order to get to this equilibrium, it requires that the strategy of the first player must be the best response for each of his type, but also for every one of his type. No. So it's not only the best response for only one type, but must be the best response in every type. Keep that in mind. That's somewhat important for you when you try to search for the Bayesian-Nash equilibrium among several candidates. Now, for the second player, because now it involves uncertainty with probability, we come back again to the expected payoff concept, which we have encountered for the first time in the game with mixed strategy, right? So instead of maximizing a certain payoff, now he will try to maximize his expected payoff. Okay, expected, if you still remember, the payoff weighted by the probability of the game occurred under each type. Okay, so the expectation here is taken with respect to her beliefs about the first player's type. What is the belief? That is, he would have a certain idea about the probability of each element in the set of the possible types of the first player. For example, it's like this, a pie chart. So this is t equals 0, which probability 1/4. Just one example different from before. And then t equals 6 with probability 3/4, right? Because the two probabilities must sum up to 1. Remember that. Okay, so he would have a certain idea about this pie chart in his head. That's called belief. And again, in this simple example, we assume that that's the true probability distribution. So that means the first player and the second players all agreed on that. But of course, they don't communicate. Okay. And using this probability that he believes or she believes, he or she will come up with the expected payoff and find a solution in order to maximize this expected payoff. With that in mind, now let's set out the formal condition for the Bayesian-Nash equilibrium. Now, if the game only has two players moving simultaneously, player 1 has private information, we talk about that. Player 2 does not. Then a Bayesian-Nash equilibrium is a strategy profile S1 start T and S2 start. Why T is here? Because earlier we said that player 1 observed his type. So the strategy he adopts will be conditioned on this type, or in math language, S1 start will be a function of T. Okay, T is taken into consideration. And why S2 start doesn't have T in there? Because it's not observable to player 2, right? So his or her strategy is unconditional with respect to T. Okay, then for the first player, this is player 1, the equilibrium required that the payoff of him or her from playing this S1 start T, given that the other player plays S2 star and T, why T is here alone again? Because earlier we also said it could affect, the T could affect the payoff directly and indirectly, right? So directly is standing alone here and indirectly through the strategy of first player. It reminds you a little bit of the envelope theorem that we had before when we had indirect objective function. No? So similar idea. Okay, so that payoff must be larger than the payoff he or she earned from playing any other strategy within his possible strategy set. Now, again, depends on T here. That is for all other strategies in his possible strategy set. Okay, that is for the first player. Now, for the second player, we have something looks a bit scarier, with involved the probability. First of all, here is the probability of type K, times the payoff of him from playing S2 stars against any S1 start depending on TK of the first player. Okay, and why there's a sum here? Because it's the expected payoff, right? Remember, expected payoff is the payoff, the weighted average of the payoff, with the weight being the probability, right? And here, namely the probability of the type that's drawn for player 1. Okay, so this expected payoff from playing the strategy S2 start must be larger or at least equal to the expected payoff of any other strategy that he or she may have in the possible strategy set. So the first line for player 1 pretty similar to the concept of Nash equilibrium that we had in the first week. If you look back, the second player, we just simply replace the payoff by the expected payoff, which is the payoff weighted by probabilities. Okay? Keep that in mind. Now, the next step will be to identify possible candidates for the Bayesian-Nash equilibrium, which is now on your slide 59. Okay, how do we do that? Actually, quite simple. We can just remember first that for the first player, it must be the best response. For a second player, also must be the best response. But now for each and every game or every type of player one, which means we could first identify the Nash equilibrium of each of these two normal forms, and then we see further, or we use them to verify if they are Bayesian-Nash equilibrium at the end. So we could just, for the first step, apply underlining procedure again. Okay, when t equals 6, there are 2 places left, then best response player 1 is to play up, right? Doesn't work. Okay, better, right? 6 is larger than 2. And if player 2 plays right, then best response is down. Now turn to player 2. When 1 plays up, then he should place left. When 1 plays down, then he should place right. So there are 2 Nash equilibrium when t equals 6. How about t equals 0? So for the first column, down is the best response of player 1 when 2 plays left. Again, down is the best response when 2 plays right. So you may realize what is down. It is the dominant strategy of player 1 in this type, right? Because it doesn't matter what player 2 plays, he should always play down. Okay, how about player 2? When 1 plays up, he should place left. When 1 plays down, he should place right. So he has no dominant strategy, just like for both in the case where t equals 6. But we still have 1 Nash equilibrium when t equals 0, which is down right. So now we identified some candidate for the Bayesian-Nash equilibrium. So remember, the strategy of the first player must be conditional on his type. Conditional means if I'm this type, I play this. If I'm this type, I play this. And you know that already from the sequential game of the battles of the sexes. So we use exactly the same notation here. For the first player, let's focus on this Nash equilibrium. So the first candidate, player 1 plays up when t equal to 6, right? Because here is when t equal to 6, so up when t equal to 6. And because it's conditional, it must have another scenario when t equals to 0. So what when t equals to 0? Because remember that player 1 has dominant strategy when t equals to 0. So it doesn't matter what, he would always play this dominant strategy if he's rational, right? So down when t equals to 0. Okay, that's for player 1. Player 2 plays where? Left, right? So So because up t equal to 6 and left is 1-Nash equilibrium. Okay. The second candidate is player 1 plays. Here's another Nash equilibrium. So place down when t equals to 6. Yeah. And again down when t equals 0. That's his dominant strategy. And player 2 plays right, because he is 1, when we underline both, is right, and here also right. So these two combinations possible Bayesian-Nash equilibrium of the game. Next step, we will verify which one is actually the Bayesian-Nash equilibrium or both. Okay, now let's check if the two candidates we just found are in this Nash equilibrium or not. How to do that will be a little bit complicated. Again, take a deep breath. So the first candidate was player 1 plays, because his strategy is conditional on his type, so always has two parts. What if the first type and what if the second type? Yeah. So we said he would play up when t equals 6 or down when t equals 0. Yeah. So it must always have something happens when t6, something happens when t0. Don't miss any of these two parts, right? And player 2 plays left, right? Because left constitute 1-Nash equilibrium with up when t equals 6. Yeah. So potentially it could be a Bayesian-Nash equilibrium, but we have to check, okay? And again, why he is only left, nothing else, not with t6 or t0, because player 2 does not observe the type. So he has nothing about that to conditional on, right? Okay, let's check. Remember the condition for the Nash, the Bayesian-Nash equilibrium, that is for both players, that must be the best response, generally. Yeah? And how to check if that's the best response? We compare the payoff of the strategy he or she played in that combination with the payoff if he had played other strategies, and why fixing the strategy of the other players or the second player at the current point. So let's do it for player 1, best response 1. Now, okay. So for player 1 it's easy because he's certain about his type and about the strategy. So doesn't have to calculate expected payoff, just simply payoff from playing up when t is 6. The first case, when t is 6. Check for its type. Because the Bayesian-Nash equilibrium must be the joint best response for each and every type. So we have to check for every type. So this is I missed something here, and player 2 plays left. Equals T6, so look at this matrix, up, left, pair of player 1, 6, right? Okay. Now compare in the same type his payoff when he plays other strategy. And here's only another strategy, which is down, right? Same type, same strategy of second player, which is left, equals T6 again, down, left. So down and left. So this is 2, right? Let's write it different colors so we don't get confused. Okay? So 6 is larger than 2. First part. Now we check for the other type. Each and every type. So check for the other type, the pair of the first player. When playing T equal to 0 now, down, right? Down. Okay. Why second player still play left? We fix the strategy of the second player at that point. Equals. Now move to the table where T0, down, left. So down and left pair of the first player is 2, right? Compared to the same type, but he played the other strategy, which is up, right? Here is down, so now it's up. Same type, T0. Same strategy of player 2 is left. Now, equal T0, up, left, 0, right? So 2 is also larger than 0. As a consequence, playing this strategy actually the best response of player 1, given that player 2 plays left, right? So let's give him a tick mark over here to indicate that that is the best response. Okay, now let's move on to check for the other player 2. If playing left is in this his best response for each and every type, given this conditional strategy of the first player. However, for player 2, the calculation will be a little bit complicated because now he faces uncertainty. He's uncertain about the type, right, of the first player. So that because of the uncertainty, we must calculate the expected payoff for him, not just payoff anymore. So expected payoff, let's denote EU2, right? Okay, now let's calculate the expected payoff of the second player when playing this strategy, when playing left. Now, left, okay? With the strategy of the first player being up when t equal to 6 and down when t equal to 0. What is that? It's just simply the payoff of the second player in these two types. When player 1 plays these two strategies and he or she plays left, weighted by the probability of each type, right? So that will be probability as the weight, right? First, the payoff when he plays left and first player plays up when t equal to 6 plus probability of t equal to 0 times his payoff when he plays left and one plays down, down. We're talking about down here, okay? Down when t equal to 0. Now, it's a little bit messy, but bear with that, okay? So we could write 0.5 again. T equal to 6, so that's second table. Player 2 plays left, okay, that's column. Player 1 plays up, so that's cell, okay. And a pair of player 2, which is 2, right? Plus the other probabilities, also 0.5 for t equal to 0 now. Now t equal to 0, move to the last table. Play left, the first column, place down the second row. So this and pair of player 2, 0, right? 0 here, okay? Which is 0.5 times 2 is 1, right? Plus 0 at the end is 1, okay? Now we compare with the expected payoff when player 2 had played the other strategy, which means right? Here we calculated left and now we turn to right. So the expected payoff of player 2 when he played right, fixing the strategy of the first player the same, meaning up when t is 6 and down when t is 0. Again, equals the probability that t is 6 times his payoff when he plays right and 1 plays up when t is 6, okay? Plus the probability that t is 0, which is 0.5, times his payoff when he plays right again and player 1 plays down when t is 0. So again, you see we fix the strategy of the first player the same when we calculate the expected payoff of the second player, and we did also fix the strategy of the second layer when we interested in the payoff of the first player. That is something useful to remember, okay? So now let's find the payoff. Okay, t equal to 6, second table, right, second column, up, first row. So that's so, right, up, right, payoff of player 2, 0. Could write 0 there, plus probability rewrite. Now t is 0, last table, right, second column, down, second row, payoff of the second player, so 4. Now, so the result will be 0.5 times 0, 0. 0.5 times 4, 2. Now, so at the end we have 2. because I got messed up again with the marker. Because expected payoff of player 2 when he plays left and the first player plays blah 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 blah. I abbreviated it now, but plays blah 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 blah. This is blah 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 blah. Okay, is smaller, right here, than the expected payoff he would have earned if he plays right. And the other plays blah 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 again, 2, right? This is not a Bayesian-Nash equilibrium. Okay, so we finished checking for the first possible strategy and show that it's not a Nash equilibrium. Okay, despite it's quite complicated, I hope I didn't lose you along the way, but still we have the live session next week, so we could answer your questions or explain again then. Okay, hopefully by then I come up with better idea about how to explain that. Okay, now let's check the other candidate to see if there's a Nash equilibrium or not. Okay. Let me cover this first. Otherwise I'll mess up again. So, okay. So same idea. First, focus on the best response of player 1 against player 2 play right. So if he play down 26 and player 2 plays right, his payoff will be 36, second table, down, second row, right, second column, this cell, payoff of the first player, so 2. On the other hand, his payoff, if he play up, right, in the same type, 6, and the other plays the same, right, would be, so now up, second table again, but first row, right, so second column, so now it's 0. So 2 is larger than 0, fine. Let's have a tick mark over here. Now let's move to let's check if his response for the other types also optimal. So sorry, not 2. You know, your brain sometimes have automatic numberings like with Excel. So 1 and must be 2 followed. But no, this is 1. We're still with the first player. So the second part of the conditional strategy, T0, down. So down when T is 0. The same strategy of the other player, right? Because we want to check the best response against right. So now T0, move to the last table, down. Oh, I I deleted this, so down. Okay, second row, right, second column. Now this cell and the first pair 2. Now, so that is 2. Similar, his pair when he had play up 20 is 0. Against the same strategy, right, of the other player would be up, 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 up the first row. Now, right, the second column, the first pair would be 0. Now, so still larger, another tick mark, meaning this is also the best response for the other type. For each and every type, player 1 has best response. That is already good from his side. Now we check for best response of player 2. Okay? By the way, I think I could just highlight this. So down. Okay, here down in different color. Then it's easier for you to see. So that is up. I have to change the color, right? And here is down. And here is up. That's how we compare. Everything else the same. Okay? Up, up, down. Okay? Okay, now for the second players, again we need to check the expected payoff to see if the expected payoff of him or her playing right is indeed the highest expected payoff in this case. Okay, so the expected payoff of player 2 from playing right while first player play down 20 equal to 6 or down again 20 equal to 0 equals again weighted average of the payoff of this strategy for each type with the weight being the probability of the types, right? So the probability of the first type t equal to 6 is 0.5 again. Now times the payoff, not the bracket yet. The payoff of second player when he plays right and the other plays down 26 in this type plus 0.5 times his payoff when he plays right and the other play down again in this type, right? And I should highlight the difference here. 6, right? Okay, so that would be 0.5 times t is equal to 6, second table, right, second column, down, second row, this cell, okay, the last cell in the second pair. So that would be 4, right, plus again 0.5 times expected payoff sorry, not expected payoff of player 2. Now T0 last table, right, last column, down, last row, this one, and second payoff 4. So 0.5 times 4 plus another 0.5 times 4, which is 4 in total, right? Now we calculate the expected payoff when he had played the other strategy, which is left. Now, given that player 1 plays the same strategy down in both types, right? Okay. Again, would be the weighted average of the type 6. Place left. And the other place down. Plus the probability of the type 0. When you place left. And the other place down again. Under this type. Okay? So that will be 0.5. This is left. And this is right. This is right. That's where the difference comes from. Right? We just deviate his or her strategy, but keep the other strategy the same, so that we could compare. Now, again, 0.5 left. So now first column, T6, so this is the right table, second table, down here, and the second pair, so that is 0. Plus 0.5 times, now move to T0, last table, left, first column, down, last row, and the second pair, so 0, which is 0 at the end. Therefore, we could conclude that expected. You see what happens when I forget to close. It's pretty inconvenient, but bear with me, please. Okay, so the expected payoff of player 2 from playing right and given the same blah 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 strategy of player 1. So now this is blah 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 is larger than the expected payoff of him if he had played left given the same blah 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 strategy of the first player, right? Therefore, this one, the second candidate, is a Nash equilibrium. Put a tick mark, and then we could say Bayesian. I keep forget that Bayesian-Nash equilibrium. So, yep, until here, you see all the steps. First, using the underlining procedure to identify possible candidate. Possible candidate is just any of the Nash equilibria in each of the type, of course, presented in conditional strategy, and then calculated the payoff of each player from playing that strategy, if the player is certain, or the expected payoff when the player face incomplete information, right? And then compare these payoff or expected payoff with what he or she may get from playing the other strategy, why the opposite player played the same strategy. And then we could compare that if indeed they have the best response, meaning their payoff or expected payoff is highest with given the strategy of the candidate, then that's a Bayesian-Nash equilibrium.